This is the Yankee-I rocket. It was supposed to be West-Tek's high-power certification rocket. Instead, it was a wake-up call. After a failed test flight, West-Tek turns to simulation software to stop guessing and start predicting. But will it be enough? Find out in today's West-Tek Solutions video. Following our Christmas trip to Tucson, we came home fired up. Seeing these larger rockets fly in person made it clear we wanted to take the next step forward in our level 1 certification. Our cousin Hansen happened to be home for the holidays, but we only had a few days before he would be shipped back to Fort Wainwright. So we did what engineers are famous for. We rushed a prototype. The Yankee-I wasn't meant to be our actual L1 certification rocket. The idea was to build something L1 adjacent, a larger, heavier design that we could fly on the 29mm Estes motors that we already had on hand. With time working against us, we modeled the rocket in Tinkercad. Ideally, this would have been done in Fusion 360, but at the time I was still learning the software and I just knew I could move faster in Tinkercad. The Yankee-I came out to a 3-inch diameter, 2.5mm thick walls, and about 36 inches tall, fully loaded around 700 grams. While the parts printed, we built the recovery system. The final L1 design will eventually use a drogue chute and a chute release, but for this prototype, we kept it simple. A single, homemade 34-inch ripstop nylon parachute.
Like that. All right, now Hansen, we're gonna tape this to your back. You're gonna jump out the second story window. And if you only break your legs, then we'll know it works. Because if you die, then it doesn't work. If you only break both your legs, success. This works pretty good.
And the next day, we were ready. Or at least we thought we were. Hansen's parents came out to watch, and Hansen was ready to launch his first ever rocket. The spirits were high. And then...
Let's just start walking backwards and I'll make the connection.
Okay.
That way we'll be sure that our cord, we'll extend our cord all the way.
Roger that. Should I wait until I feel the gust stop? Because obviously the wind just picked up. Now once I the blasting cap in,
Wait for the red light.
and then I see the red light.
Yep. Then you can launch. Red light means
That okay?
That means you're
Like nothing's gonna happen. I'll start counting down.
Yep.
Because that means I'm ready. I'll start
check
counting.
the airspace.
Yeah.
Make sure it's clear. You don't see or
Okay.
hear anything. You're good.
Okay.
And then when you're ready, you push that red button.
Okay. All right.
I think it's going to be windy either way. I think that this thing's going to go. This thing,
Okay.
I don't have a ton of confidence we're going to recover this one.
All right. On your command.
All right.
5, 4, 3, 2, 1. Uh-oh.
Hey, retain the chute.
So what went wrong? Well, if you watch the footage closely, you'll notice the fins catching the wind almost immediately after liftoff. Instead of climbing straight, the rocket pulls back and turns into the wind. That's called weathercocking. Some weathercocking is normal. This wasn't normal. This was a rocket that was severely underpowered for its weight. The Yankee-I exceeded the E16.6 motor's recommended maximum weight by nearly double. Any basic analysis, or even just reading the motor's datasheet, would have made that obvious before we ever hit the launch button. Instead, we learned it the hard way. In the wake of the Yankee-I disaster, we had to confront an uncomfortable truth. We don't really know what the hell we're doing. Up to this point, our approach had been pretty straightforward. Build something, launch it, and hope for the best. And that works until it doesn't. And standing over the wreckage of the Yankee-I, the gap between what we knew and what we needed to know felt enormous. But here's the thing, that feeling is actually a good sign. What we were experiencing is something called the Dunning-Kruger Effect. In short, it describes how beginners often overestimate their competence, while people with more experience become painfully aware of how much they don't know. Confidence peaks early, then drops off a cliff once reality sets in. West-Tek had officially entered what is known as the Valley of Despair. We had learned just enough about rocketry to realize we don't actually understand rocketry at all. And while that's a demoralizing place to be, it's actually an important milestone, because you can't fix what you don't know is broken. So how do you climb out of the Valley of Despair? Well, you learn. If we wanted to make sense of future flight performance, we needed to stop guessing and start predicting. That meant learning simulation software and confronting a little bit of math. There were a few options out there for rocket simulation, but the one that we landed on was OpenRocket. OpenRocket is an open source simulation program that lets you model a rocket from the ground up. Geometry, mass, motors, recovery systems, and simulate its flight before it ever leaves the rail. It predicts stability, velocity, altitude, and deployment events, and it's widely used in hobbyist and educational rocketry community for exactly this reason. It turns intuition into numbers. At first, the software felt pretty overwhelming. While looking for help, I stumbled on the Rocket Noobs video series, and he just made learning the software an absolute breeze. So I'm going to leave some links down below to his videos, and I highly recommend that if you're interested in learning more about OpenRocket Sim. And I have on good authority he's a subscriber to the channel, so it's not, not a big deal. Not a big deal. Suddenly, we had a tool to understand past failures and plan future launches with real data instead of just gut feelings. So what does OpenRocket say about our past flights? After recreating the Stratus in OpenRocket, the simulation lined up perfectly with our real-world results. On a D12.3, smooth and safe, just like in the field. On a D12.7, the simulation flagged exactly what we'd already seen. The rocket was already accelerating downward when the parachute deployed. And the Yankee-I? The simulation predicted an apogee of just around 200 feet with deployment dangerously close to the ground. No surprises there. The key takeaway is simple. For both flights, OpenRocket would have predicted exactly what went wrong. A little pre-flight number crunching would have saved us money, time, and a lot of shredded parachutes. Well, now that we had the tools to predict flight performance, we went looking for a chance to redeem ourselves, and that's when we found the Upstate Research Rocketry Group, a rocketry club within driving distance that runs winter launches, and they happen to be hosting one that weekend. So we rallied to see if we could make something fly using what we had on hand, a few of the remaining E16.6 and F15.6 motors. Reading through the club's safety rules, one requirement jumped out: a strict 5-to-1 thrust-to-weight ratio. Clubs enforce this to make sure rockets leave the rail fast and stable, reducing weathercocking and the chance of a dangerous low-altitude failure. The Stratus, at 335 grams, cleared that bar easily on E16.6. No problem. The Yankee? Not even close. So we got to work. By removing the entire body section, shrinking the parachute, shortening the payload bay, and reprinting parts at criminally low infill percentages, we got the weight to just over 500 grams, barely clearing the 5-to-1 thrust-to-weight ratio on an F15.6. The result was a drastically shorter rocket, same 3-inch diameter, but now 27 inches tall instead of 36, and we called it the Yankee Mini. At these new specs, OpenRocket finally returned acceptable results. Thrust-to-weight ratios the club would sign off on, and on paper, everything checked out. Well, now there's only one thing left to do: see if the simulations were telling the truth. We drove out to the URRG on a cold Saturday morning. The club launched out of a wide open field, and when we pulled up, there were already a handful of people setting up. Everyone was incredibly welcoming, and we met a couple of guys named Rich and a man who went by Gray Squirrel. These were people who had clearly been doing this for a long time, and they were genuinely excited to see new faces, and it was a great reminder that this hobby has one of the best communities out there. So we prepped both rockets, the Stratus on a E16.6 and the Yankee Mini on a F15.6. Numbers checked, sims run, thrust-to-weight ratios verified, and for the first time, we weren't just hoping. We had data on our side. So first up was the Yankee Mini.
We got Brendan West's West-Tek Yankee flying on an F15.6. This is a first flight, so keep your eyes open. Going up in 3, 2, 1. Oh, not good. Well, closest to the block.
I think we blow up more rockets than we launch these days. It's the head coming off, I think.
Okay. These videos tend to follow kind of a formulaic path. We have we set up a problem, there's some sort of setback, and then at the end, the resounding climax, we overcome the problem in some magnificent way. So obviously, this is the part of the video where at least the Stratus flies successfully. So let's take a look at that footage.
We've got Bob West's West-Tek Stratus Heavy going up on an E16.6 in 3, 2, 1. Oh. Not having luck. It was the E16 that I blew up on too.
this with some of the bigger ones. If they freeze cycle, it sometimes shrinks the powder and it creates cracks in it.
Oh wow.
That is.
Oh yeah, that's hot.
So what the hell? I mean, we did everything right. We ran the simulations, we got the ratios, we got the club approval, and both rockets still just KO'd? Well, that's a lesson you don't learn in any simulation. Some things are just outside your control. You can model aerodynamics, predict stability margins, calculate thrust curves down to the decimal, and a motor can still just blow up on the launch pad. There is no simulation for that. And at some point, you do have to just light the fuse and accept whatever happens next. So where does that leave us? For now, we're putting the L1 certification on hold, and instead we're going to step back and develop a mid-high power rocket with a proven flight record before we try to go any bigger. Basically, we're holding ourselves back a grade on purpose. As for the bigger lesson, simulation is necessary, but it's not sufficient. We learn simulation to avoid failure, but failure is still a necessary part of the process, and it's unavoidable. You can't simulate your way out of every problem, and eventually you have to fly. And sometimes that means crashing. But here's the thing about West-Tek. We're not just in the rocketry business, we're also kind of in the entertainment business. So, these failures, they're not really like setbacks necessarily, they're content, right? So the failures are kind of the business. So if you think about it that way, you can say business is good.
That is.
Oh yeah, that's hot.
It's